Previously, we talked about the electric force. This meant that when there were more than one force, we could see how they interacted. If they were like charges, they were repulsed from each other, because the force pushed them apart. This means that the force only exists when there's more than one charge. And since it's a 1 over r squared law, if the charges are far apart, it's essentially like there's no force at all. This means that the charged object has an influence in the space around it. This influence permeates the space around the object in all directions, just like gravity does with masses. So even when there is no second charge, there's still an electric influence surrounding any other charge. We call this the electric field. For a spherical charge, the electric field is going to spread out in all directions, getting weaker and weaker as it goes. Now, if it were a negative charge, all these lines would be going towards the charge instead. This means if we bring in a small secondary test charge, we can see what direction it wants to move away. Since they're both positive, it moves along the field line away from the main charge. If we bring in a negative charge, it now has an attractive force, so it wants to go towards the big positive charge. Notice that the electric field line and the direction of the force are opposite for negatives. So otherwise, negative charges go against the field lines. This is convenient because we can use the field lines of the electric field to describe complicated situations of charges without having to deal with messy equations. What we see here is two metal plates. The top one has a positive charge and the bottom one has a negative charge. So the field line wants to go away from the positive and towards the negative. And it does this throughout the middle of these plates. So if we were to bring a small electric charge in here, it would want to move against the field lines and go straight up towards the positive plate. Other arrangements of charges are possible. Here we have what is commonly called a dipole, where a positive and a negative charge are in close proximity. The field line's going away from the positive towards the negative. If we were to add a negative charge right here, per se, it would go against the field lines, follow it all the way down towards the positive. And likewise, if we added a positive, it would go with the field line towards the negative. It looks a little different if both the field lines are the same. Here we have two positive charges. Notice that the field lines are moving away from both of them. Right here in the middle, a field line would be going away from that charge, and another one would be going away from this charge, and they cancel out. This means there is no electric field right there where they equal. So if we were very careful and put a charge right here, it would feel no force from the other two. So a negative charge right here would stay put, and a positive charge would stay put. Now, if we put a positive charge here like a proton, since there are field lines in that and it don't perfectly cancel, it would shoot out through the top. An electron, which is negative, would go against the field lines, get some velocity momentum, which means it would fly past the 0 point and start to slow down again, so it would oscillate back and forth between the two. For a single charge, the electric field is actually decently easy to calculate. So the formula for it, we use a capital E with arrow over it because it's a vector field, so there's a direction and a size. So the E field, as we call it for short, is equal to Coulomb's constant times the charge over r squared. Remember, the charge is in coulombs, and K is 9 times 10 to the 9 newtons times meters squared per coulomb squared, which means the units of an electric field is in newtons per coulomb, or how much force a given charge will have when it encounters a second charge. This means if we know the electric field and we want to know what the electric force is when we bring another charge in close, all we have to do is take our test charge times the electric field, which would give us our familiar equation. For example, say we set up an electric field 8.0 times 10 to the newtons per coulomb. What force would an electron experience in this field? So we take the force, it's just the charge of the electron, times the electric field we were given. So that's going to be negative 1.6 times 10 to the minus 19 coulombs times 8.0 times 10 to the third newtons per coulomb. Again, you notice that the coulombs cancel out, leaving us with just newtons, which is what we want. So this gives us approximately 1.3 times 10 to the negative 15 newtons in the negative direction, which seems small, but keep in mind that electrons are very small, so that's actually a lot of force. Now we can reverse this. What if we wanted to find the electric field? Well, all we have to do is find the electric force and divide it by the charge. So some key equations: the one for the electric field by itself, how the force is connected to the electric field, and how to do the reverse are things you should keep in mind. As always, check your units. It'll make sure you did the algebra correctly.